This lesson is going to continue our work on compound inequalities with a focus on the special cases, situations that maybe don't play the way we normally would expect these compound inequalities to play. So we know now that a compound inequality involves either an and or an or statement. And traditionally, for the most part, when we look at those, they either shade toward each other in an and statement, and we're looking for that overlap, or they're shading away from each other in an or statement. And it's just, solutions to either side of that work. So those are the ones that we discussed in our last lesson. Today we're going to talk about what happens if they don't necessarily play by the rules, if you will. If maybe we start off with an and statement, but for example here they both end up, the both inequalities end up going in the same direction. What does that look like? Or perhaps it's an and statement, but at the end, once you solve it, you realize they're shading away from each other. And that means that although our steps are going to be the same as what we've been doing, our solving steps are still going to be everything, that we've been practicing for multiple lessons now. None of that changes. Our answers, we're going to have to be extra sort of in tune with what is the true meaning of our answers to decide what is the best final answer for that problem. So it's a little bit less about the computation, because that part isn't going to be any different from what we've been doing, but it is going to require a higher level of analysis to really interpret and understand what your final solutions really are to that compound statement. Okay, and there's one here already done for you. We have this first example. It is an and statement. It's not written together because they're like different operations, but it's still an and, which basically says that our solution in the end is any values that make this inequality and that inequality true. So in other words, the overlap. Okay, so that's what we're still going to be looking for. The word and is my key word here to know that at the end, I'm only interested in the final answer where my graphs overlap. So you can see here the steps are the same. We decide to gather our x's to one side. So it looks here like they subtracted x and got x's on the left. And once you did that, you got to the answer. So one of our solutions is any x's that are less than -1. And you can see that they graph that here. Anything less than -1, that now individual inequality is graphed right there. On the other side, it requires a little bit more work. You could distribute this 2, or you could divide it out since 10 is divisible. So it looks like they just divided by 2 here. Got that 5. This is out of the parentheses now, and then they added the 9. I'm sorry, they added the 4 to get the 9. And then they rotated the statement. So in this inequality, it's all the x's less than or equal to 9, which is this one here. So this is one of those odd cases. They're not very common, but sometimes they happen, where my and statement ended up with 2 inequalities that shade in the same direction. So how do I know what my final answer is, right? One is saying all the values that are less than -1. The other one is saying all the values that are less than or equal to 9. Well, that's decision is really all about the fact that I want an and type of situation or an and statement. So I'm only interested in values that are true for both, that are less than -1 and also less than or equal to 9. So if you think about that, that's still, our focus is still where those graphs overlap. So even though on this top one, I start having solutions here at 9, there is no overlap here. So basically over here, neither of them have solutions, right? Nothing works over here. Starting at number 9, only one of our inequalities works. So in an and statement, that's still not enough, right? But then we get here, and starting here, I have values that work in both. So values, for example, like -2, I can plug that in here and it works. -2 is less than or equal to 9, and it also works here. And so that's an example of a value that is in my solution set because it works in both. So I'm still looking for that overlap. So once I kind of compare, even though they're going in the same direction, in an and statement, I'm always going to end up keeping usually it's the smaller section where they both are true or where they both overlap. So my final answer is just, okay, well then the solution to that and statement is only x's that are less than -1. Because anything that works here will work in both. Okay, but not everything that works here works in both. So it's got to be this one. So that's an example of a special case. And see how we really had to kind of just think about that and reason out which solutions actually made sense. So let's actually solve our own. This one is an or statement, so let's pay close attention. So I don't need them to overlap. Anything that makes one or the other true will work. So obviously we have to do a little bit of solving here to find out what our solutions are for each one of these. So let's start with the one on the left. Some like terms that I can combine here. I've got a 9 minus 4x, which I know is 5x. So I can combine some like terms there. This side is fully simplified, so I'm just going to bring it down. But it doesn't have any like terms, and it doesn't have any grouping symbols that I need to simplify. Step 2 is take care of those x's, right? So I have x's on both sides, so I'm going to try to get rid of that problem as quickly as possible. So I'm going to go ahead and pick one of my x terms and eliminate it with the opposite sign. In this case, I'm choosing to do the 3 for a variety of reasons. First of all, I like my variables on the left, and I also like them positive. So it's a win-win to get rid of the 3 x's. So that now leaves me with 2 x's, because if I take 3 away here, I have to take 3 away there. So I've got 2x minus 5 is greater than or equal to 5. Now it's really just a two-step equation. That's a 5. It's a two-step equation, and now I can start isolating my variable. So I'll start by moving the 5 this way, by adding it, cancel it there. Greater than or equal to, now I have a 10. And then we divide both sides by the 2, and we are finally at our first inequality. Okay, so x is greater than or equal to 5. So if I were to graph this, let's say I put 5 here somewhere, okay, that if I just graph that one, this is not my final answer, this is just the first one, I want any solutions that make this true. So anything that is either 5 or greater than or equal to 5. So that's that solution. Or anything that makes this guy true. So let's find out what makes that true. Okay. And so here, again, a little simplifying is in order. So let's go ahead and distribute here. I'll get 6x plus 2. Like that. Okay. And then I'll move my x's because I have x's on both sides. And again, I like to keep them positive and on the left. So I'm going to go ahead and move them. Get rid of the 5x. Some people get a little nervous because there's nothing else there. They don't think they can do that. Of course you can do that. If there's nothing else left, well, let's say that with a 0. That's okay. It's worth it because look how easy this is. It was totally worth it. You could have moved the 6 this way, but then it would have been negative and it would have been on the other side and you would have had to fix a few things. So I think this is better because now all I have to do is subtract 2 and I am ready to go. So our solution here is all the x's greater than or equal to -2 for the second inequality in this compound statement. Okay? So let's graph those options. So those options would be at -2. So this is 5, 4, 3, 2, 1, 0, -1, -2. There's. Okay. So then I would have anything that is -2 or greater than. Okay. Now, those are the two individual ones. I want to know what is the solution to our entire compound statement. So I want anything that makes one or the other true. So I want you to notice the difference between this one and this one. If it had been an and statement, I would only be interested in where they overlap. So my solution would start here with the 5. But in this or statement, as long as it's true for at least one, we're good to go. So that means my solutions can start all the way here. It's basically my longer arrow. So, anything less than -2 does not work for either one, so nothing there. But starting at -2, I have solutions that work in at least one of these, okay? And as long as it works in at least one or the other, we're fine. So I don't have to narrow it down, and I don't have to be so restrictive as to like, oh, they have to overlap. They would have to overlap in my final answer if I wanted an and statement, but this is an or. So everything starting from -2 and on. So my final solution is essentially this longer line. Anything, so my final solution here is the x's that are greater than or equal to the -2. Where over here, it was only the overlap, so it was only the x's less than 1. Right? So in an and statement, if they're going in the same direction, in an and statement, it's going to be the shorter, overlapping, more restrictive option. And in an or statement, is as soon as you start getting solutions, that's enough. As long as there are solutions to at least one. Okay? So the yellow here is our final solution to the entire compound statement. All right, let's try another one. Go ahead and switch over to the other side here. Let's try number 13. This is an and statement, so you can see how important it is as we're interpreting our final answers to really be aware of what kind of statement we're working with. So this one's an and statement. So we'll solve each one, but my solution set needs to be the region or the set of values that make both of them true. So keep that in mind. So let's start on this side here. To simplify this long division bar, I'll start off by multiplying by 3 on both sides to cancel that division. And that's going to leave us 7x minus 5. That is greater than or equal to 9. Okay. And now it's just a nice two-step equation. I'm going to go a little bit faster through this process. At this point, I think we all know how to solve. Okay. Greater than or equal to 14. And then we divide both sides by 7. And so we get x is greater than or equal to 2. So if I were just to, explore what would that look like and on our number line, for example, let's say I have 0, 1, 2. So the solutions here are any values that are either greater than or equal to 2. So that solution would be headed this way. Okay, so I'm just going to mark that. That's not my final answer. I'm just kind of making a mark on it. All right, let's solve the other side. I don't have grouping symbols, but I do have variables on both sides. So let's go ahead and take care of that. I'm going to get rid of the 3x. I like to have them on the left, but I also like them positive even more. So I'm going to just go ahead and do that, and then I can rotate my statement. So I've got 1 is greater than or equal to x minus 1, and then I just add 1. So this is 2 is greater than or equal to x. I don't like the way that looks. We've talked about that. So rotate your statement so that it is so that it has a variable on the left. Okay. So on this one, we have all the x's that are less than or equal to 2. So if I were to graph this one independently, it would be everything that is less than or equal to 2, which would go in this direction, right? But wait, this is a very interesting graph already, first of all. And what really we need to keep an eye on is this. I only want solutions where these guys overlap. So if I look at the two graphs and I compare them, there's only one. Oh, wait a minute. I just realized what I did. I put my dots on the wrong spot there. So sorry. Let's put that here. I don't know why I did that. So glad I caught that before I kept going. Okay, so it should be everything greater than or equal to 2. And this one wants everything that is less than or equal to 2. And I'm only interested as far as a solution to the entire compound inequality. It's only what makes them both true. When I look to see where these guys overlap, they literally overlap at exactly one place only. And that is at 2. That is the only place I have overlap on these graphs. So very interestingly enough, this compound inequality has one and only one solution possible. And that solution is x equals 2. It is the only place where they overlap. Anything here works in one inequality but not the other. Everything over here works on the other one but not the first one. And here is the only time that they are in agreement or that they overlap. So x equals 2 is a solution there. So very interesting. You see how each case you kind of just have to think about if it's an and or an or statement and kind of process what your solution should be based on that. And interpret it, do a smart analysis, if you will. Let's try number 14. Again, I'm going to go through the solving steps a little bit faster because that part we should already be comfortable with. This is an and statement, so once again, I'm looking for where they overlap. But first, let's solve each one. So I'm going to start by solving this one here. Nothing to simplify, so I'm going to get rid of my x. I've got negative 18 is less than x minus 23. And then we'll add 23 on both sides so that these guys cancel. And that's a difference of 5, if I'm not mistaken, is less than x. Do not love the way that looks, right? We know that we do not want our variable on the right side, so I'll rotate that. And I realize, oh, it's really the x's that are greater than 5. So if I just kind of make a small note to myself here as I am graphing these, let's put 5 right there. It's going to be an open circle and anything greater than that. Let's actually put that a little bit higher since that's not our final, but we'd be looking at as anything there. Okay, so we'll put a pin on that. Let's solve this one. We'll add 16 on both sides, and this one's a little shorter. We get x has to be less than negative 6. Okay, so all the x's that are less than negative 6. So that's over here, negative 1, negative 2, negative 3. I should have thought this through a little bit better. Negative 5 and negative 6 would have been like over here. Just to extend that a little bit. But more importantly, I want all the x's that are less than that, like strictly less than it. So there's that solution. But wait a minute. This is an and statement. So these ended up shading away from each other. I want anything that is either greater than 5 or anything, and less than negative 6, right? And if it's an and statement, I want any numbers that make both of these true. But as you can see very clearly and obviously, there is no overlap here at all. There's nothing that makes both of these true. It can be greater than 5, or it can be less than 6, negative 6, but it can't be both at the same time. And so there's no overlap here. Even though this is a fine inequality, if it's an and statement, this has no solution. The compound inequality here has no solutions that work because there are no solutions that will satisfy both of these inequalities at the same time. So in the end, I just leave my number line blank and I just say this has no solutions. I'll never be able to come up with a number that is greater than 5 and also less than negative 6. It just does not work. So that's a no solution right there. Okay. All right, let's just try one or two more and then we're going to wrap it up. I'm going to go even faster a little bit because you can now tell that the work we're doing here is all review and all the same. It's really what happens that afterwards, as far as interpreting, that you really need to be alert for and really analyze. So a little bit faster here. I'm going to solve for y. This is an and statement. I'll move the 3. And then I also need to take care of this negative. So I'm going to go ahead and divide by a negative 1 on both sides so that my y is positive. That's going to flip my sign. And then this is our first inequality in this and statement. Okay. And then for the next one, we just have this guy here. All we have to do is subtract 2 and then we're good. So y's that are greater than 7. Okay. So there is my 2 different solutions. Let's go ahead and graph them and see what happens. I think I'm trying to be a little bit smarter about my graphing here. I'm going to go odds. So negative 1, negative 3, negative 5, negative 7, and then 1, 3, 5, 7, 9. Okay. And so then I want all the y's that are either all the y's that are greater than or equal to negative 5. So that's here. Greater than or equal to. And also greater than 7. So also greater than 7. Okay. So these guys, they shaded in the same direction. Okay. And it's an and statement, so that's what I really want to be careful. If this had been an or statement, my solution would be anything that started here, because starting here, there's a solution to at least one of these. But since it's an and statement, I need it to be true in both. I'm looking for the overlap, and that doesn't start until after the 7, right? So this inequality right here, the y is greater than 7, is my final graph for this compound inequality. That's the final graph right there. And it basically means that this is what satisfies the compound inequality. Any value that is greater than 7 will also be greater than or equal to -5. So it makes both of them true. But not every value that's greater than -5 works here, right? So I need it to work in both. Then I'm interested in, this section here where they start to overlap. Okay. All right, let's finish out with number 17. That's our last one. 17, again, this is an or statement, so I wanted to make sure we did at least a couple of those. I know we did one on the front. Or statement, so as long as it's true for one or for the other, then we can include it in our final solution. So here, to solve, we'll add 6. We'll get x is less than or equal to 9. Or if we solve this side, we'll get rid of that 2. We'll get rid of that 5. That'll give me 2, and then I'll divide. And I'll get x is greater than 1. So my solutions here need to be anything that is less than or equal to 9, or anything that is greater than 1. So let's take a look at what that final solution looks like. If I go ahead and graph this, again, I'm going to go 2, 4, 6, 8, 10. That should be okay there, just to have enough room. So I want anything that is less than or equal to 9. So 9 would be right here. So that one would be less than or equal to, with shade in this direction. Or anything greater than 1, which is over here. So anything greater than 1. That shades that. So these guys shade toward each other, but it's an or statement. So I want anything that makes one or the other true. So I want you to think about that. Look at your graphs. I want it to be true for just at least one. It doesn't have to overlap. It doesn't have to be both. So what would our solution be here? So if you think about it, hopefully you said everything. Every number is either going to be larger than 1 or less than or equal to 9, right? These guys are going in both directions. And if I only need at least one of them to be true, then at least one of them is always true, right? Here they're true for both. So if if it had been an and statement, this is the only part that I could actually use. But if it's an or statement, then everything in this direction forever toward that negative infinity, it works on this top one. And everything going on toward positive infinity works over here. So in this case, the entire number line is our solution, and it's basically all real numbers. So there's lots of different examples there for special cases and how you just interpret each one as they come, depending if it's an and or an or statement, and what your graphs ended up looking.